Good morning, teachers and our fellow mates. So, today our group is going to be presenting on the topic pulsars. The other members of this group are Nirupan Thapa and Aryanjali Sharma. So, our topic is divided into three parts. The first part, that is the origin of pulsar, would be presented by me. The second part, that is the formation and functioning of pulsar, will be presented by Nirupan Thapa. And the third part, that is the detecting gravitational waves with the help of pulsar, will be presented by our Anjali Sharma. Origin of pulsar. The discovery of pulsar. The first pulsar was observed on November 28, 1967 by Joselyn Bell Bernal and Anthony Hewish. They observed pulsars separated by 1.33 seconds that originated from the same location in the sky and kept to sight real time. In looking for explanation for the pulses, the short period of the pulse eliminated most astrophysical sources of radiation, such as stars, and since the pulses follow sidereal time, it could not be human-made radio frequency interference. When observation with another telescope confirmed the emission, it eliminated any sort of instrumental effect. At this point, Bell Burnell said of herself and Hewish that we did not really believe that we had picked up signals from another civilization, but obviously the idea had crossed our minds, and we had no proof that it was an entirely natural radio emission. It is an interesting problem. If one thinks one may have detected life elsewhere in the universe, how does one announce the results responsibly? Even so, they nicknamed the signal LGM1, that stands for Little Green Man. Next slide, please. The existence of neutron star was proposed by Walter Baade and Fritz Zwicky in 1934. The existence of neutron star was first proposed by Walter Baade and Fritz Zwicky in 1934 when they argued that a small, dense star consisting primarily of neutron would result from a supernova. Based on the idea of magnetic flux conservation from magnetic main sequence stars, Ludwig Wolzer proposed in 1964 that such neutron star might contain magnetic field as large as 1014 to 1016 GeV. In 1967, shortly before the discovery of pulsars, Franco Pacini suggested that a rotating neutron star with a magnetic field would emit radiation, and even noted that energy could be pumped into a supernova remnant around a neutron star, such as the Crab Nebula. After the discovery of the first pulsar, Thomas Gould independently suggested a rotating neutron star model similar to that of Pacini and explicitly argued that this model could explain the pulse radiation observed by Bell, Burnell, and Hewish. In 1968, Richard V. Lovelace, with collaborators, discovered period P32 ms of the Crab Nebula pulsar using Arecibo observator. The discovery of the Crab pulsar provided confirmation of the rotating neutron star model of pulsar. The Crab pulsar 33 millisecond pulse period was too short to be consistent with other proposed models for pulsar emission. Moreover, the Crab pulsar is named because it is located at the center of the Crab Nebula, consistent with the 1933 prediction of the Baade and Zwicky. In 1974, Anthony Hewish and Martin Riley, who had developed revolutionary radio telescope, became the first astronomers to be awarded the Nobel Prize in Physics. Next slide. So, what is a pulsar? A pulsar is a highly magnetized, rotating compact star that emits beam of electromagnetic radiation out of its magnetic pole. This radiation can be observed only when a beam of emission is pointing towards Earth, similar to a way a lighthouse can be seen only when the light is pointed in the direction of the observer, and is responsible for the pulse appearance of emission. Neutron stars are very dense and have short regular rotational periods. This produces a very precise interval between pulsars that range from millisecond to second for an individual pulsar. Pulsar are one of the candidates for the sources of ultra high energy cosmic ray. The period of pulsar make them very useful tool for astronomers. Observations of a pulsar in a binary neutron star system were used to indirectly confirm the existence of gravitational radiation. The first extrasolar planets were discovered around a pulsar PSR B1257 plus 12 In 1983, certain types of pulsar were detected that at that time exceeded the accuracy of atomic clock in keeping time. So I conclude my part. I would like Nirupan to continue. Thank you.
Good morning, teachers and fellow friends. I hope my audio is clear.
It's clear, Nirupan.
So my part is the formation and functioning of pulsars. So basically, a pulsar is the core of a star that has collapsed into a neutron star. They spin very rapidly and also have very strong magnetic fields, which produces powerful thin beam of radio waves. They're extremely dense stars composed entirely of neutrons with diameter less than 20 kilometers or less. So in this diagram, you can see the pulsar rotating on its axis, and the magnetic field lines rotate along with the pulsar, and the magnetic field lines are originate from the north and south pole direction, and they produce radiation beam which shoot across the space. And this is the module of how the pulsar rotates on its axis. You can see the radiation beam originating from the magnetic field lines. The formation of pulsars. You can see the diagram of a star. This is the original star, and this is the core of the star, and this is the outer crust. So inside the core of the star, there is a powerful fusion reaction taking place, and this fusion reaction produces heat and pressure that supports the star against gravitational collapse. The force of gravity acting on the outer surface of the star is always trying to push the star inwards, but the fusion reaction stops the star from collapsing. So this is what I'm talking about. The gravitational force acting on the outer surface of star is always trying to push the star inwards, but the fusion reaction taking place at the core of the star is always trying to push the star outwards. So the forces cancel out each other, thus this preventing from the star from collapsing. So near the end of the star's life, this core runs out of fuel for its fusion reaction. The fusion reaction is going to eventually stop. So what happens when this occurs? The star goes supernova. The core of star can no longer support itself against gravity and very rapidly collapses down into a very small size. When this happens, a huge amount of energy is given off, so much energy that the outer layer of a star is violently thrown out into space, and this phenomenon is very well known as supernova. So if the star that went supernova has the correct mass ranging about 8 to 20 times the mass of the sun, then when the star collapses, we'll get a dense remnant neutron star, which is this. And if the mass of the star is less than 8 times the mass of the sun, then the full compression won't take place. The core of star will just collapse into a white dwarf star. An example of a dwarf star is our planet, not the planet, our sun. If the mass of star is more than 20 times the mass of sun, then the core of star has enough mass to further collapse down all the way down to a black hole. Massive stars died in their own huge gravity, leaving behind black hole. So you can see the images of black hole taken in different years. So the mass of neutron star or core of star is about 1.5 to 3 times mass of sun, but they are only about 25 kilometers in size, about the size of an average city, which means they have huge amount of mass, but relatively small space. If you can compress the entire mass of Mount Everest in a small backpack, you would be very close to the density of the neutron stars. The only other place in the Earth, the only other place in nature that we find density like this are in the atomic core of atomic nuclei. So the neutron star acts like a giant atomic nucleus, and inside the core of a neutron star, we still don't know what form matter takes place at such immense density and pressure. These objects are so small and massive, their surface gravity is about 200 billion times stronger than the surface gravity on Earth. When the star collapses into a neutron star, there are two very important things happen. The neutron star that starts to spin very rapidly, and this due to conservation of angular momentum. So So the neutron stars so formed, the remnant neutron stars so formed, have a very rapid spin, and this is due to conservation of angular momentum. It's the same thing that happens to us when we spin around in the same spot with our arms held outwards, and when we quickly pull our arm inwards, we start to spin faster. So this is the star we originally started out with. It has some spin to it, but after supernova explosion, the remnant neutron star starts to spin very rapidly, which is due to conservation of angular momentum. For instance, our sun takes 25 days per one spin, and when it collapses, the huge amount of mass gets pulled in, just like how we pull our arm inwards to get more spin velocity. The same thing that happens to us, that happens to the star after supernova explosion. The remnant neutron stars so formed starts to spin very rapidly. Most pulsars can spin once every second, taking 1 second per one spin. There is another class of millisecond pulsars which spin 100 times per second, taking 10 milliseconds per one spin. Some of these millisecond pulsars can spin as fast as a blender, therefore giving very high spin in some of the neutron stars. The original star has some magnetic fields, but these magnetic fields will compress along with the remnant neutron star, resulting in some extremely powerful magnetic fields. And as they rotate along with the star, they produce a powerful beam of radio waves that shoot out from the north and south pole of the neutron star. In general, the direction is not along the same axis on which the pulsar rotates, but it's quite slanted and or tilted towards the north and south direction. So this is how the pulsar rotates. It's the module. It's quite slanted towards the north and south pole. It's not on the same. It's not perpendicular like the rotational axis on which the pulsar rotates. Only if the neutron star is oriented in the right direction to our planet, then every time the neutron star rotates, we can see little bursts of radio waves for a short time, and we can detect and measure it using radio telescopes. So this is the normal type of pulsar, and these are the frequencies. So this is the first pulsar, PSR BO329 plus 54. This pulsar is typical the normal pulsar, which rotates about average taking 1 second per one spin, and this is how it sounds like. Now this is the second type of pulsar, the Crab pulsar. This is the youngest known pulsar, and it lies on the Crab Nebula, the supernova remnant of its birth explosion, which was witnessed by Europeans and Chinese in the year 1054 AD as a daytime light in the sky. The pulsar rotates about 30 times a second. So it's the sound of pulsar. And this is the third type of pulsar. This is the millisecond pulsar. So it rotates about 174 times per second. So as you can hear that the pulsar does not produce at each beat because the spin is so high that we can only hear constant sound. So these pulsar signals can be exceedingly stable and regular, most notably for the fastest rotating millisecond pulsars. And for some of our best pulsars, we can predict an individual pulse is going to when the individual pulse is going to occur years ahead of time to an accuracy of 100 nanoseconds or 1/10 millionth of a second. This incredible timing accuracy can sometimes rival that of atomic clocks on Earth, especially over long time scales. And it is this property that allows us to use the pulsar signals basically as kind of celestial clock. And each one of these pulses are the ticks of this clock. So this concludes my presentation on formation and functioning of pulsar. So with any further ado, I would like to our third member, Aryanjali Sharma, to continue with the presentation.
Is my screen visible, sir?
Yes.
So good morning, respected teachers and my dear friends. I would be elaborating more about pulsars and its importance. I would like to dedicate this presentation to Bell Burnell, whose works have inspired me to do this presentation.
Aryanjali, if you
She
are
was the
using
first
two
person who
different
discovered.
this thing, you have to mute one of your devices. If you are logging from two different devices, you have to.
Sir, I can't hear you.
Aryanjali, can you hear me? Aryanjali?
Yes, ma'am.
Okay, so sir is saying that I think you have logged into two devices.
Yes, sir. Yes, ma'am.
So you
You
have
have
to
to
mute
mute
one.
Harish Sharma, where this
Hmm.
presentation one. Mute that.
Yes, you mute her, yes. Sound? Sound is coming. Huh?
Ma'am, could you just wait for a minute? Some
Yeah, no
problem is going
problem.
on up here.
Yeah,
No
it's
problem.
working though. It's no longer echoing.
Hmm.
Yeah, mute the. Okay. The mic that you're using to speak, that needs to be unmuted. Everything else needs to be muted. Only the mic that you're using to speak needs to be unmuted. Mute everything else.
Sound is there?
So is the screen visible?
Yeah, screen's visible. Your voice is coming through clearly. Go ahead.
Okay, yes, sir. So good morning, respected teachers and my dear friends. I would be elaborating more about pulsars and its importance. So I would like to dedicate this presentation to Joselyn Bell Burnell, whose works have inspired me to do this presentation. She was the first person who discovered pulsar in 1967, but she did not receive the Nobel Prize. Sir Martin Ryle and Anthony Hewish received the Nobel Prize in Physics in 1974 for their decisive role in discovery of pulsars. From Earth, pulsars often look like flickering stars on and off. They seem to blink with a regular rhythm. Pulsars belong to a family of objects called neutron stars that form when a star more massive than the Sun runs out of fuel in its core and collapses in on itself. Pulsars radiate two steady narrow beams of light in opposite directions. Although the light from the beam is steady, pulsars appear to flicker because they also spin. The existence of gravitational waves was first predicted by Albert Einstein in 1916 in his general theory of relativity. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe. The strongest gravitational waves are produced by events such as colliding black holes, supernova, and colliding neutron stars. The first direct observation of gravitational waves was made on 14 September 2015 and was announced by the LIGO and Virgo collaborations on 11 February 2016. Nanograph searches for gravitational waves using something called a pulsar timing array. A pulsar is a special kind of neutron star that spins around very quickly and shoots out beams of radio waves. Whenever a pulsar spins around, it shoots the radio wave towards the Earth, which we measure as a radio pulse. Pulsars are very reliable and we can very accurately predict when the radio pulses will arrive at Earth. This means we can use pulsars like a stopwatch with which we can mark the passage of time by the number of radio pulses that have been observed from a pulsar. Pulsars are great stopwatches that stay reliable over many years. If a gravitational wave crosses the space between Earth and a pulsar, it will stretch and squeeze that space. If a space is stretched, it will take longer than expected for the radio beam to reach the pulse. The pulse will arrive late. The opposite is true. If space is squeezed, because the radio pulse will arrive earlier than expected. We can subtract our predictions of when the radio pulses should arrive from our real observations and look at the difference. That difference could be due to gravitational waves. Nanograv have been using radio telescopes to observe lots of pulsars to make a big net that can catch gravitational waves. Scientists have confirmed the identity of the youngest known pulsar in the Milky Way galaxy using data from NASA's Chandra X-ray Observatory. A team of astronomers have confirmed that supernova remnant Case-75, located about 19,000 light-years away from Earth, contains the youngest known pulsar in the Milky Way galaxy. This pulsar is about 200 million years old. Among isolated pulsars, it is over 10 times older than the previous record holders with an X-ray detection. At a distance of 770 light-years, it is one of the nearest pulsar known. It is the fastest spinning pulsar at 716 times per second. It is at a distance of 18,000 light-years. Located some 5,200 light-years away from the Earth, this pulsar is a rotation-powered pulsar, which means that the loss of rotational energy of the star provides the power from the radio emission. It has a spin period of approximately 23.5 seconds, which makes it the slowest spinning pulsar. Pulsars can be used to search for dark matter, pulsar-based time standards, galactic magnetic field, interstellar field, and interstellar medium, and it can also be used to confirm extrasolar planets. Thank you.
Okay, well done. Do any of the students have a question?
No, sir.
Okay. You may also type in your questions if you have difficulties using the mic. Okay. First, for some comments, Pewang, can you show Pewang's the first presentation? I think Nirupan was presenting it, right? Okay. Nirupan, can you just show Pewang's presentation? Right, yeah. Can you just, yeah, actually, this is good enough. This is called a Cardinal Sin in presentations, right? And this is something I mentioned back in the demo class. You cannot have a huge block of text in a presentation and you cannot put a huge block of text in a presentation and then make people read the entire thing. That is a no-no in presentations. You're not supposed to do that. So there are times when it's okay to put a big block of text on the screen. For example, in a previous presentation, which is the one that the Mars presentation, they put the picture of an article which had a huge amount of text where the abstract was. But at no point did Rudranil or anyone talking about the presentation, at no point did they talk about the abstract or point out the abstract. See, when they put that paper on the screen, you are not expected to read the abstract. It is just there. But here, not only do you have a huge block of text, you're also expected to read the text because the person who's presenting is reading out everything word for word. So two things that you should not do in a presentation is put a huge block of text and make the person read everything. And number two, after putting a huge block of text, read out every word in that text. It is considered to be a strict no-no because people start getting bored. This is a psychological thing. People just don't want to read a huge amount of text on a screen, right? And the big thing is there are, I think, 3 or 4 different slides where it's just one big block of text after the another. So this is the big sort of the issue with this presentation. For example, go to slide 4. So big block of text, go to slide 5. Big block of text, go to slide, with smaller font, go to slide 6. And then big block of text. So if you put a huge amount of blocks of text, with sort of no breaks in between, you're totally going to lose your audience this way. See, don't take this as like, oh, you did bad or anything like this. This is a issue that I have done when I first started making presentations. This was a big problem that I did. This is a problem that a lot of people do when they first make presentations. You do not want to remove information because you think all of it's important, and you put up so much information on the screen. But the problem is that people like watch the presentation, they're not going to want to read all of this, especially if you put a whole bunch of them in a row, right? On the other hand, in the second presentation that Nirupan had, he did not have big blocks of text for the most part. He was putting points. And not only was he, so Nirupan, go to your second presentation. Yes, Prajal sir is also saying he used to do it like this and he learned it later. We've all done this. We have all done like huge amounts of text in the screen. And then later onwards, everyone's like, yeah, it was a good presentation, but I didn't follow all of it because, the brains turn off when they see all the things. So there was one point, I think it was your slide number 2 or slide number 3, where you have those points coming one by one, right? Is it this one? Can you just play the slides again? Yeah, this one. See, notice, not only does he have points, he has it in points, so you don't have a big block of text, but keep going through the animations. He does not show all of it at once. See, you don't see all 3 at once. So suddenly you don't have this huge amount of text on the screen. He does it one at a time. So your brain only has to look at a little bit of detail, a little bit of information at a time. So this is kind of how you want to arrange text. So if you have a lot of text to show, like you have to show a lot of text, don't show it as one big block. This is where you actually use animations and transitions. Show a little bit at a time. Okay. So Nirupan, I don't know if Nirupan was the one who made this presentation, but yeah, this is like a good way. And you can see that then you put the GIF and all of that. And one thing is you kind of skip through the GIF pretty quickly, but that's fine. Aside from that, the presentations are good. And obviously this is something that is very close to my heart. I really like anything to do with cosmology and astronomy. And this is and pulsars is one of my favorite topics. So I quite enjoyed this presentation and I liked it. I think I had a question, but now I've completely forgotten about it because I wanted to talk about all this. It's fine. There is a question from Subayu, which is, how come a pulsar, which is made up of neutrons, have a magnetic field? Actually, that is a question. That's a good question.
Right.
That is actually a very famous question.
So I think I'll answer that. Hello?
Yeah,
is my audio clear?
Yeah, Nirupan, go ahead.
So for any elementary particle to have any intrinsic magnetic moment, it must have spin and electric charge. So the neutron has spin but has no charge. So the neutron is composed of 3 quarks, and the magnetic moments of this elementary particle combine to give the neutron its magnetic moment. I think that I said that in brief.
Yes, Nirupan, you're right. Just to expand on what Nirupan says, so fundamentally neutrons are made of quarks, and each quark has either plus 1/3 charge or minus 1/3 charge. Now, neutrons are made up of 3 quarks where the charges, sorry, I'm trying to remember from memory. It's I think what, 1 down
So
and
plus 2/3 and minus 1/3.
yeah, it's plus 2/3 and minus 1/3. Is it 1 down and 2 up, or is it 1 up and 2 down? Anyway, whichever. The charges cancel each
1
other
up, 2
out.
down.
1 up, 2
down,
down. Up is plus 2/3 and down is minus 1/3. So they cancel each other. But as the neutron undergoes quantum spin, the 3 quarks sort of move about a little bit, combine next to each other. So because they're moving about a little bit, they form a magnetic, you can imagine them making a magnetic dipole, which just create a very tiny magnetic moment. And that, of course, gets magnified when you go across the whole star. So while a neutron is electrically neutral, it is not always necessarily magnetically neutral, which is a big discovery back in the day, I think, when they found the neutron's magnetic moment. Okay, but yeah, Nirupan got the thing right. It is because of the spin that sort of gives it a magnetic moment. I actually don't have any other questions. I had a question, but I completely forgot, so I won't waste time remembering it. So I don't have any other questions. Just one last thing, you guys did really well, aside from the slight issue with the presentation, but I quite liked it.
Am I audible?
Yes, sir.
Yeah. To add to that, yeah, it was very good. Is there any reason for making 2 separate slides? Was there any issue with the technicalities?
Yes, sir. Actually, Siddharth wanted to present it, but he had some technical issues with the computer, so I had to present it.
No, I'm asking that Aryanjali's slide was totally separate one. You could have put it in the same thing. Anyways, that didn't cause any harm. Yeah, it was a very good presentation. Yeah, what sir said regarding Pewang's part, yeah, I don't want to repeat that. So yeah, from next time, it should not look like very, monotonic. Like very simply, it should not be like I'm using a software to read from PDFs. Okay, whatever is written, you are just revising that. Apart from that, everything was very good. The choice of background color and the animations. I think GIFs you put, right? All GIFs, I think.
Yes, sir.
Yeah. And one question, I'm curious to know the sounds that you made us hear. Kind of
Yes,
first
sir.
one was like a metronome. Then you said that the beats have been converted to continuous things. So
Yes,
are
sir.
these sounds in the original form, or are these have been exaggerated? I mean magnified
Sir,
or
I think so. These are not the original song. These have been amplified, or they are artificial songs, I guess.
I mean, have they been magnified, or they have been minimized in the intensity? What do you think?
So the beats, I think they are. So it's not the original beats from the Pulsar.
Yeah,
I think
I'm asking, is the original sound too loud than this one, or very faint than this one?
they are faint.
Okay, fine. And yeah, with Aryanjali's presentation, the good thing was like that dedication part. I'm asking because of that, because the dedication part should have been, had this been a single slide, at the beginning only Joselyn's portion would have been put forward. Anyways, it's a very good thing. And did you go through any limit of size of a star above which it can, cause a supernova, and below which it can become a white dwarf or something? Have you gone through
Yes, sir.
anything?
I
Is
just
there,
went.
yeah,
I shown
is there
that.
any limit to the mass of the star? Is there any name?
So the total, the max, the exact weight, sir.
No, the name, the limiting weight. Okay,
No
Rudra is
idea.
There is a
answering.
limit to the mass of the star, which is very famous. It's
Yeah.
named after a very famous person.
Okay, Rudra, you're asking or telling?
So I'm pretty sure, but still,
Yeah,
that
yeah.
1%
Nearly
probability of being wrong.
1.4 times the solar mass. Okay, very well done. And I think the reference section was missing. You can put that. Otherwise, I felt that the script was very well recited, very well compiled. There were no, semantic errors, grammatical errors, I felt. And okay, very well done. And next time, I think you all will take care of these technical issues.
Yes, sir.
Because the only reason to I don't know, some of you might feel this thing bit tormenting, bit strenuous, is that to present you as a very presentable presenter in the future in front of vast audience. Okay, and in our college, the audiences are mostly, multicultural, multilingual, diversified. Yeah, okay, so Shubhayu has another question.
So this is the question, right?
Yeah, that would be the question.
What happens when a neutron star becomes more massive than a size you told? Size. So, so if the mass of this, so I didn't quite get the question. What happens when a neutron star becomes?
So I think his question is there any change to the properties of the star if it starts to gain mass? For example, one of the stars that you mentioned said that it was taking mass from a binary, it was part of a binary system and it was taking mass from its companion star. So his question would have been like, is there any change to a neutron star? Does it change into a different type of a star? Or does it still behave like a neutron star? Something like that.
No, I think, sir, the neutron star has a specific mass for the formation of neutron star. The formation of pulsars, I mean to say, it has a specific mass. It can't go if the mass is more than it might. It will become a black hole. So it will collapse down to a black hole. To become a neutron star, there should be a specific mass, like as a classified here. It has to be 8 to 20 times the mass of the sun. So the neutron star has some specific conditions.
Okay, just for Subhaya, I'll just expand on the answer. So, by the way, a pulsar can also be created by a white dwarf. They are much more rarer, but white dwarfs can create pulsars. It needs a very specific conditions to occur. A neutron star, as Nirupan was saying, a neutron star requires a certain specific mass to occur. There needs to be a range of masses for a neutron star to occur. After a neutron star has occurred, if it manages to accrete mass, which means that it is taking mass from somewhere else, usually there's a star nearby and it just siphons mass off from the star. There will be, at one point in time, it is quite possible for it to gain so much mass that it undergoes an implosion and then becomes a black hole. So there are cases of neutron stars becoming black holes because they gained masses later. Basically, if it takes in more mass, more and more pressure occurs on the core because everything's trying to collapse inwards gravitationally, but there no longer is any fusion occurring to push out the mass. So if there's enough mass, everything just implodes inside, and then everything collapses into a black hole. This was, I forget the name, but there are black holes that we know were previously neutron stars. Right? So that's what happens. If you get enough mass, a neutron star will become a black hole. If you don't get enough mass, generally it depends. Usually the neutron star starts rotating faster, which is, I think, what happens, which is one of the stars they talked about. What happens is the orbital angular momentum of the companion star gets transferred to the rotational angular momentum of the neutron star, and it starts rotating faster. So that's another thing that happens, and then your pulses get faster and faster and faster. And this is another thing that was observed as well. They observed a variation in the pulses of a neutron star across multiple years. So that's another thing that's happened.
So any other questions?
Okay, from my side, I have no questions. I have just few comments that you are using your arrow, but there in the PPT, in the presentation, PowerPoint, there is a feature called laser pointer. You can use that.
Yes, ma'am.
And your presentation, the slides, everything was wonderful. It was a very, very good presentation. Means not only of yours, Nirupan, Aryanjali, Pewang, everyone of you, you have done very well. And yes, as the Merck sir said, if it is just a compact PPT, then it will look better. Okay, so next time don't break the PPTs. If there is any technical problem, then it's not an issue. And otherwise, you make a single PPT. Okay.
Yes, ma'am.
Okay, that's all from my side.
Okay, no questions from my side as well. So it was a marvelous presentation. And yeah, the reason why we are wanting compact or we are wanting to collate the PPT or a single PPT from your side is that one thing is that it will streamline the flow. So when you present, the others don't have to close the tab and then open a new PPT. Another most important thing is that like in one case we had only the text that was described there in the PPT slide, which we do not want. Okay. So had it been among your groups, had it been a single slide, one of you could have commented to your fellow mate not to put it like that. So that way also it will help you in bringing up with the good slides. So each one of you can comment on your way of presentation when you collate it and then make it a single one. Okay, had you done that, so we could not. It would not have been this way, I believe. But anyways, it was a good presentation, and yes, you have to refrain from adding so many texts. Okay, you do not want your audience to get bored.